So thank you for the introduction. Thank you a lot for your great talk, which helped to set the stage. And thanks a lot for organizers for putting the fantastic lineup together in this workshop. So my name is Helena REICHLOVA, and you see that I will speak about work which was done partly in Prague, but also a lot of the work was done in Dresden. And as an experimentalist, of course, the work was done in broad collaboration. You see a lot of familiar names here, including Sebastian, and hopefully we will also soon start to work with Matthias. So Matthias already introduced basically everything. So the Spintronics with antiferromagnets is a blossoming field. And I also like to mention that, yes, the general curiosity is what is probably driving most of us, but there is also some kind of justification from the application that the antiferromagnets do have many advantages over the ferromagnets, such as the absence of the stray field, the faster intrinsic frequency. But what I like most, and I will also mention it during the talk, is that there is actually more materials available, that there are intrinsic semiconductors which are antiferromagnet available. And we remember, or some of us remember, how much effort we put to combine the ferromagnet and semiconductor. And in the case of antiferromagnets, it's already a very natural thing. So, but yes, the antiferromagnets are useful. So what are the spintronic effects which we know in antiferromagnets? And here, let me just summarize the thing which you learned from Matthias already, that the anomalous Hall or anomalous Nernst effect was observed and now is pretty routinely observed in many antiferromagnets. It was driven by the group of Satoru Nakatsui and Claudia Ferser, and then followed by many others that indeed it's already established thing. From the application perspective, it's more important to think about, let's say, this tunneling magnetoresistance or tunneling anisotropic magnetoresistance. And here again, a lot of work was already done. And we talk about the small tunneling anisotropic magnetoresistance. It was shown already around 2012, when it was shown that these non-collinear systems can be separated by some insulating barrier to a non-magnetic electrode. And then indeed one can observe some spin valve-like signal as shown here. And lately, in the last year, it was also shown that it can be this tunneling magnetoresistance, as Matthias showed, between two non-collinear antiferromagnets. And one more thing, which from, let's say, the application perspective, spintronic effect is important to mention, is the gigantic magnetoresistance, the effect which started the field of spintronics, which is shown as the kind of wonderful example of how quickly it made it to application. And the gigantic magnetoresistance is, let's say, one thing which we could here put not with a check, but with a question mark, because it's predicted, right? It's predicted from Jakub Železný that indeed it should work. It should work also in these non-collinear antiferromagnets as shown here. But experimentally there was significant effort, but without like this clear success. And there are many reasons for that. Let's say the interface should be perfect and so on. But this gigantic magnetoresistance is still some sort of open question, which in these antiferromagnets it's not so well established as in the other phenomena. And so these, when now we look at this choose or some couple of these key spintronic phenomena, we see that the thing which they share in common is that they were all observed on these non-collinear systems. And now when we kind of go one step back and say, okay, so is this really true that the collinear systems for this most standard spintronic phenomena are kind of not predicted? Is this really something which we should accept? And then, let's say when I still did my PhD, it was indeed the case that none of these effects would be expected in the standard collinear antiferromagnets. But things changed, and also here, thanks to the Mainz and the Prague theory teams, they sort of revisited the idea of the collinear systems. And now when we look at such a square, the most simple square lattice, and then we can sort of revisit the classification as we understand it. And when we start from the ferromagnets, which are the workhorse of industry, right, they have this nice, strong polarization given by their strongly aligned spins. And then when one look at the K-space, this polarization of the electronic bands then breaks the time reversal symmetry, and this leads to phenomena such as this giant magnetoresistance responses, which are then desired by the application. And they also don't mind that there is some net magnetization and that they are mostly metals because they simply work, and yes, this is what we have with ferromagnets. In the same time, the antiferromagnets are, let's say, having many disadvantages in the sense that in the collinear case, they do not break the time reversal symmetry in the K-space because the spin bands up and down are degenerate. However, they are having this potential for very fast intrinsic frequencies. And also, as I said, there is more materials available, and also in the context of, let's say, this neuromorphic computing, the antiferromagnets are showing the ability to have this multiple stable states, which is very much desired. So yeah, there is also a lot of potential for antiferromagnets, but this kind of absence of the robust spin polarization is a clear disadvantage. And then, as Matthias mentioned, the effort driven by Libor Šmejkal showed that there is yet another class, which is still in the let's say, universe of simple collinear systems. And this is just by considering also the non-magnetic environment of such a simple square lattice. And by this anisotropic oxygen cages, let's say, which are not connected by some inversion or translation, but by the rotation in the real space, it translates to the momentum space as the splitting of the electronic bands with the opposite polarization in such a fashion. And when we then look in this sort of 90-degree cuts, then we see that the spin polarization is alternating, leading to the suggested term altermagnets. But what is important for the spintronic research, that this kind of energy cuts, which I was showing before, okay, yes, now are not degenerate anymore, and depending on the crystal direction, we can see that there will be excess of the spins up or spin down, leading to all these effects which rely on the spin polarization. So coming back to this table, we see that the altermagnets are combining the properties of the ferromagnets and antiferromagnets, and on top of that, they have this characteristic anisotropy, which is something which is unprecedented in the ferromagnets and antiferromagnets. So this is the very brief summary, also what you learned from Matthias already. But then let's look on some experimental examples, right? So there is now, I would say, almost boom of experiments on altermagnets. And the most natural thing how to look at something which has a very specific features in the electronic bands is to look at electronic bands, right? So the spectroscopy, the angular resolved spectroscopy is the direct evidence, is the thing which now brings like a lot of fascinating results. And Matthias was showing the work of Juraj Krempasky, where in the Mangantel, right, we were showing that indeed one can observe the calculated alternating splitting of the spins in the momentum space. And it's not the only work. There are also a few other works either on arXiv or already published. So let's say the spectroscopy is a direct evidence, but me as a spintronic person, of course, tend to think in terms of, let's say, transport or magnetothermal transport. And then the first thing which one would say is the simplest to think about, when one does not need any interface, one does not need to directly go for some tunnel junction, is to take a simple piece of material which we have and try to measure effects which do rely on the breaking of the time reversal symmetry, which is the characteristic feature which distinguishes them from the conventional antiferromagnets. And so this anomalous Hall effect is exactly effect which needs the breaking of the T-symmetry in the momentum space. And in this talk, I will try to go through few works which we did on altermagnetic materials. So before that, just like a very small recap, so anomalous Hall effect refers to a voltage measured perpendicular to both the applied current and some magnetic order vector, and ideally it demonstrates as some sort of spontaneous signal with a saturation field. And now, as I mentioned, it's now already sort of established that it can be observed in many of non-collinear antiferromagnets, that it does not relies only on this ferromagnetic materials. And what is important to note is that indeed in this conventional antiferromagnets collinear, because of the TT is a symmetry, as when you see that when you flip the spin and translate it by a half unit cell, we recover the picture. But when we now consider also this anisotropic non-magnetic environment, we cannot do the same exercise by flipping the spin, and we cannot translate it by any half unit cell to recover the original image. So therefore the TT is not a symmetry, and we do expect, so based on Libor prediction here, that the anomalous Hall effect is allowed in these altermagnetic materials. What is important to note is that unlike in ferromagnets, where we always have allowed anomalous Hall effect, in the altermagnets it naturally depends on the orientation of the null vector if the TT is broken or not, and therefore it can be highly anisotropic. So let's look at some concrete altermagnetic candidates. So these are three materials which we have some experience with. And here the workhorse ruthenium dioxide altermagnet I will not cover because I guess that Matthias will cover it. So Matthias already explained that how the ruthenium dioxide breaks the symmetries and how is the anomalous Hall effect observed there. However, we have also other two candidates which from experimental perspective we tend to like even more because I will explain you that unlike in the ruthenium dioxide, where the null vector in the zero magnetic field is just in the orientation when it does not allow for the anomalous Hall effect. In these two materials, already in the zero magnetic field, we can have anomalous Hall effect, and therefore we can observe a spontaneous signal. So these are two materials, and let me start with the mangan telluride. So here, mangan telluride is one example of a semiconductor which is in the same time altermagnetic. And when I say semiconductor, it's a real semiconductor. It's not something which is basically metallic like some of these semiconductors which were ferromagnetic. So here it's a beautiful semiconductor which is well known to the community, so it can be also grown in very high quality in this by the MB grown on the indium phosphide, and these hexagonal planes have these tellurium cages around these manganese atoms, and when we just look at some of these two manganese with the opposite spin, and we look how the tellurium cages look around, we see that it's not a simple translation, but it's a translation combined with the rotation. And this is exactly what fulfills our altermagnetic criteria. At the same time, when we measure the magnetometry, we see that it has perfectly or almost perfectly compensated, that there is a vanishing net magnetic moment. And calculations, again, from the Mainz team show that the anomalous Hall effect is indeed allowed. So from some mangan telluride thin films, we patterned Hall bars, and we measured the transversal and longitudinal voltage. And this, as I showed you on the previous slide, the spins are basically in the plane of the manganese, but the Hall vector is in the out of plane, and it can be linked to the external magnetic field, so we can control it by external magnetic field. And here I show just the magnetoresistance, which looks pretty conventionally. But when one measures now the transversal response, in the hole geometry, we can see that it's dominated by the ordinary hole. This is the strong linear slope. But when the ordinary part, the linear part here is subtracted, we can see that what is left there is a clear opening, a clear hysteresis, which is present there also in the zero magnetic field. And you see that it depends indeed on the out-of-plane component, because it can inverse or it flips when we do the magnetic field sweep along 30 and minus 30 degrees. So this looks already pretty nice. And now when we take one of these here, the kind of suggestion is that it indeed corresponds to two opposite null vectors of the mangan telluride. And when we now take one of these anomalous Hall curves, we define something which we call spontaneous anomalous Hall, which is present in zero field and some saturating, and we can plot it against the temperature. We can see that indeed it's present in the full temperature range until, let's say, room temperature, which is also the critical temperature of our mangan telluride. This was some time ago, it was already 2 years ago, and since then it was reproduced by a couple of groups, and also not only in thin films but also including in our groups. We can now see this anomalous Hall effect present also in this bulk, like you see very dirty experiment just putting like 4 wires into a piece of mangan telluride, and we can observe the anomalous Hall effect there. Again, I said a few other groups already confirmed that this is present there. So this is mangan telluride. It's a nice thing. And then another candidate which I will talk about is the mangan 5 silicon 3. It's a little bit more complicated here because in the bulk this compound is known to undergo several structural transition which is accompanied by a magnetic phase transition from this room temperature high temperature phase, high temperature collinear phase to some non-collinear phase at the lower temperature. However, when this material is grown by MBE on a silicon substrate, the epitaxial constraints actually stabilize this hexagonal unit cell, which is in the bulk allowed only in the room temperature phase. And the stabilization of the hexagonal phase we also confirm by temperature-dependent structural studies. So we see that the C parameter, which is the out-of-plane parameter, is changing with the temperature because this is not constrained by the substrate. However, the AB parameters, which are changing in the bulk compound because there is no constraints from the substrate, are not changing in the thin film. So we have the hexagonal unit cell in the full temperature range. And this we also confirm by TEM things, by TEM results, and this allows us also to see that we have a different phase of mangan silicon, which I will then show in more details in the following. But what we did is that we patterned Hall bars, we measured transversal longitudinal signal, and you see that we also observed that the critical temperature was shifted because, again, of the strain up to the 240 Kelvin. And when we check the magnetometry, within our resolution, we are not capable to see the moment, so it's somewhere, let's say, below 20 millibor magneton per manganese in the full temperature range. The transversal signal, and we can see that there is a clear, robust, spontaneous anomalous Hall response, which is present until this 240, and then it's absent in the paramagnetic state. So this is some experimental evidence. And then let's just look at it. So what we know, so we learned that experimental evidence for the hexagonal unit cell, we have experimental evidence for vanishing magnetization, we have experimental evidence for some spontaneous time reversal symmetry breaking because we do observe anomalous Hall effect. And in the same time, we know that our thin films are stabilized to this hexagonal unit cell in the full temperature range, which again allows us to compare it to the bulk material. And we see that the thing which in the bulk is the TT, it's a symmetry. It's not symmetry in the thin films, because here again we can do the exercise to flip the position, the magnetic color, let's say the red to the blue, and then we see that we cannot do any translation operation to recover the original image. So again, the TT symmetry is broken here, which again fulfills the altermagnetic criteria by slightly different mechanism, right? Because here no rotation is involved, and therefore it's a strong hint that our spontaneous anomalous Hall indeed originates from the altermagnetism. And so in the remaining part, I will just talk about one more thing. When we already have our mangan 5 silicon 3 films, we also, here, let me just skip that because I would not have time for it. And here I will just mention one more thing, that the anomalous Hall effect is also highly anisotropic compared to let's say, ferromagnets, where we would observe, where we would expect some cosine-like dependency of the anomalous Hall effect. Here, in this case, when we do angular dependency, we rotate the magnetic field in the out of plane to in plane. This is the signal which we are measuring. And you see that there are some characteristic features. First is the asymmetry of the trace there and back, the clockwise, anti-clockwise, and also this highly sort of anisotropic plateaus in the characteristic shapes. And here, I think that maybe without going to too many details, there are two things to note. First is that it's kind of absolutely not correlated with the SQUID data, with the magnetometry data, so it directly excludes some ferromagnetic-like origin of our anomalous Hall effect. But also this highly anisotropic anomalous Hall effect points that it's not some simple ferromagnet-like origin of the anomalous Hall effect, but indeed that this high anisotropy again points towards the altermagnetism origin, as detailed, for example, in the paper here of Mina Lejvska, and also Helena will not talk about it, but or will but at some point probably. Good. So and then last thing which I wanted to mention is that I mentioned the anomalous Hall effect, but there is also the counterpart, the anomalous Nernst effect, right? And this is just replacing the electrical current by thermal gradient. We do expect almost the same signal. And why I mention it is that this anomalous Nernst effect is actually very interesting also, not only for some elegant way of harvesting heat, but also as a magnetic microscopy tool, as Matthias was explaining, that by showing that there is the anomalous Nernst effect, one can get access to doing some magnetic microscopy also in systems which are otherwise invisible in some conventional magnetic microscopy techniques. And one more thing which I want to mention is that there is now kind of search for efficient materials which do have high anomalous Nernst coefficients, and typically it relies on some heavy elements. There are fantastic works from the environment of Claudia Fersel from Japan, which, however, very often rely on some uranium or ytterbium, like heavy elements, which indeed then lead to the very high anomalous Nernst coefficients. However, but from what I explained to you, that in our case the origin of the spin splitting is not related to the spin-orbital interaction. It's relying on this altermagnetic splitting by the non-magnetic environment, and therefore the idea is that we don't need heavy elements to have significant anomalous Nernst coefficients. And yes, this was then, of course, natural to think, let's test it in our mangan 5 silicon 3 films, because these are some of the lightest, most abundant elements which we can have. It's directly on silicon, it's directly thin film. So let's try to measure it. So this is the experimental setup which we had. We have our thin films. We have macroscopic heater on one side and some good heat sink on the other side. So we develop a thermal gradient. Here, this part I will skip, but just to kind of tell you that to quantify actually the gradient is significant more work than to actually measure the anomalous Nernst effect. And what do we see is that here it's an example of our data. So the black curve is the anomalous Hall effect from our mangan 5 silicon 3 films, and the orange data which are on top of it is the anomalous Hall effect. So indeed, we also see that it has the same anisotropy, the same characteristic increase of the coercive field with increasing temperature, and it's in a good agreement with the theory, again provided from our colleagues from Mainz. And now, as the last slide, I just put the values which we measured here in our alter magnet to a table which compares different materials. And here the different materials mean really ranging from the antiferromagnets to ferromagnets, which are marked by the open circles, and by the size of the ball, I indicate how heavy the element is. And now, when we look at the magnitude of our Nernst effect, we see that the record large are indeed these uranium-based compounds. This is wonderful work. Then here, the ytterbium one, again like a very large coefficient, but still very heavy element. Here also, you see that it's a small, so it means that it's a heavy element. And then in the next let's say line, we have already the cobalt-2 mangan gallium ferromagnetic topological ferromagnet, where it relies on the relatively fragile contributions from the intrinsic anomalous Nernst effect. And then we are almost already in our range where we have our simple mangan silicon thin films compatible with the silicon. So this just shows the potential that the first try on this lightweight elements, and we already have a pretty solid anomalous Nernst effect. So this brings me to the conclusion, and I will just leave it here for the questions.